quality. So generally, the ambient air quality is the general amount of pollution present in a broad area. So the atmosphere's average purity as distinguished from discharge measurements taken at the source of pollution. So air pollutant, so quick overview from air pollution. So air pollutant means any matter found in the atmosphere other than oxygen, nitrogen, water vapor, carbon dioxide, and the inert gases in their natural or normal concentration. So this is according to our Constitution, the Clean Air Act of 1999 or the RA 8749. So we've already studied three of the air pollutant sources. So we have mobile sources, stationary sources, area sources, but we also have natural sources. So there are three types of ambient air contaminants. So we have criteria pollutants, we have air toxics, and biological pollutants. So criteria air pollutants, these are air pollutants that have been regulated and are used as indicators of air quality. So they are generally widely distributed across the country. So we have carbon monoxide, lead, nitrogen dioxide, ozone, particles or total suspended particles or TSP, and sulfur dioxide. So what these are the indicators of air quality here in the Philippines. Now, so how do we describe particulate matter? So we know that human hair, it has a very small diameter, so it is actually 50 to 70 microns or micrometer in diameter. Also, beach sand or fine beach sand has a 90 microns in diameter. Now, we have two types of particles. We have PM 2.5 and we have PM 10. So, in PM 2.5, these are combustion particles, organic compounds, metals, and etc. So, it has a 2.5 microns or less than 2.5 microns in diameter. While PM10 or particulate matter 10, PM10 are those of dust, pollen, and mold, and etc. So those have 10 microns in diameter. So we also have air toxics. So this is referred to as hazardous air pollutants. So it can lead to an increase in the incidence of cancer, birth defects, genetic damage, central nervous system defects, immunodeficiency, and disorders of the respiratory and nervous system. So I've mentioned a while ago that how sulfur dioxide can also cause irritation to the lungs as it forms sulfuric acid. So this is also an air toxic. So, but we have these air toxics are what is being monitored. So we have formaldehyde, benzene, toluene, xylene, and polycyclic aromatic hydrocarbons or PAH. So this is according to US NEPA. Next, we have biological pollutants. So from microbiological contamination like molds, the skin of animals and humans, and the remains and droppings of pests such as cockroaches. So these can be airborne and can have a significant impact on indoor air quality. So we know that molds actually can cause irritation to the nose and such. So what are the ambient air quality parameters? So what are we looking at when we check for ambient air? So we have physical, chemical, and biological. So in the physical, we have the TSP or the total suspended particles, the odor, and the visibility. In the chemical, we have toxic fumes and etc. And in biological, we have the presence of pathogens. So that's it for ambient air quality parameters. Now let's move on to the control of air pollution. So most air pollution control mechanisms are designed for gaseous pollutants and particulates. So in large-scale industries, they usually air pollution control is controlled. Air pollution is controlled uh, in the basis of in the design. The design is based on gaseous pollutants and particulates. So treatment schemes for gaseous pollutants include absorption, absorption, adsorption, and combustion, flaring, or oxidation. So in gas absorption, so a unit operation to separate gases by washing or scrubbing a gas mixture with a suitable liquid or a scrubbing liquid. An example would be a flue gas desulfurization or FGD that is usually employed to remove sulfur oxide in outlet gases. So you can find this in chemical plants that have sulfur dioxide as their byproduct. So this is the chemical reaction. So uses chemicals such as lime, limestone, caustic soda, soda ash, and ammonia to remove sulfur in gas. So the absorption systems include, so we have a Venturi scrubber, we have static bed packed bed reactor, moving bed reactor, tray towers, and spray towers. So I think you are familiar with these. These you can find in chemical industries or manufacturing plants, usually that have byproducts of gaseous byproducts. So let me show you a Venturi scrubber.
Venturi scrubber. Air quality control is important to the success of every business, especially ones with industrial applications. The best way to maintain a high level of air quality is by using dust collection equipment. Dust collection equipment improves air quality in your facilities by removing harmful pollutants that can endanger workers, put your regulatory compliance at risk, and damage equipment. Air quality solutions have moved beyond typical dry dust collection, using the inherent properties of the impaction process to create wet scrubbers. Wet scrubbers rely on scrubbing fluid to remove dust from an air or gas stream. One of the most powerful and widely used types of wet scrubber is the Venturi scrubber. While Venturi devices have been used for over 100 years to measure and record fluid flow, it wasn't until the late 1940s that engineers learned to use Venturi design to efficiently remove particles from airstreams. Venturis are able to do so through their hydro-friendly designs. In order to clean air, Venturi scrubbers use the differential between high-velocity dust particles and free-flowing fluid such as water to create contaminant entrapping water droplets. Venturi scrubbers are designed to efficiently remove fumes, dust, solids, and aerosols. The scrubbing liquid, most commonly water, comes into contact with the particulate-laden gas stream in a highly turbulent, high-velocity Venturi throat. As the droplets and particulate matter interact, they agglomerate in the diverging section of the Venturi. The entrained droplets, contaminated with the particulate matter, are removed from the gas stream by means of cyclonic separator. The cleaned gas exits the cyclonic separator, while the recovered scrubbing fluid is returned to a separate or integral tank for recirculation. By selecting the appropriate pressure drop, which is proportional to the throat velocity, efficiencies of over 99% can be achieved over a wide range of particle sizes. Although standardized in size and capacity, each individual unit is custom designed and engineered to meet the specific requirement of each application.
Alright, so that was the Venturi scrubber. I also have an example here, packed bed scrubber.
A packed bed scrubber, also called packed tower scrubber, is designed to remove both particulate matter as well as gaseous pollutants. The contaminated gas stream is fed into the tower. Inside the tower is a bed of special packing material. Nozzles spray scrubbing liquid on top of the packing material, and the liquid works its way down the tower. As the gas passes up through the packing material, the particulate and gas molecules come in contact with the film of scrubbing liquid on the packing. The contaminated liquid drains down through the packing material, past a packing support, and out through the bottom of the tower. The gas stream flows out through the top of the packing material, past the nozzles, and through a mist eliminator before exiting the tower.
So that was the packed bed reactor. Or scrubber, sorry, packed bed scrubber. So a packed bed scrubber can remove particulate matter and as well as gaseous contaminants. So in a packed bed reactor, as you have seen for a while, packed bed scrubber, I keep saying reactor. In a packed bed scrubber, so as you can see here, there is a, what you call this, there is a packing material. So this packing material also helps the gas to not only go straight, but it also traps particulates in the packing material. It also creates a longer time for the gas to be soaked in the scrubbing liquid, since it has very many crevices and gas could travel in different ways through this packed bed. Alright, so that is a packed bed scrubber. So those are examples of gas absorption systems. So next system is we have the adsorption of gases on solids. So what is adsorption? So adsorption is different from absorption. So adsorption is when particulates or uh, any matter or any matter is uh, is stuck on the surface, only the surface a um, of a material. So an example would be activated carbon treatment. So this is a popular air pollution control method. So this method sees the use of dry chemical scrubbing media such as carbon filters for the adsorption of fumes from the air. So it uses dry chemical scrubbing media such as carbon filters. That's what adsorption of gases on solids. So this is an example. So uh, this is a porous carbon. So vapor molecules over time, so they heat. All right. So vapor molecules go inside the crevices of a carbon molecule. So the vapor also gets stuck inside, and once once the vapor is, or the crevices are full, um, heating the carbon is one way of cleaning it. You can also introduce steam to clean the carbon material, and it is ready to be used. So unlike absorption with the use of liquid scrubbers, so this could actually be used again. So sometimes the scrubbing liquid, it is already hard to separate, to treat the scrubbing liquid again for it to be used. But some still do that. But in this case, like the activated carbon, so you only steam it or heat it for it to regenerate. All right. So an example of the system would be a pressure swing adsorption. So a pressure swing adsorption processes utilize the fact that under high pressure, so high pressure, gases tend to be attracted to solid surfaces or adsorbed. So the higher the pressure, the more gas is adsorbed. So when the pressure is reduced, the gas is released and desorbed. So the PSA processes can be used to separate gases in a mixture because different gases tend to be attracted to different solid surfaces more or less strongly. If a gas mixture, such as air, is passed under pressure through a vessel containing an adsorbent bed of zeolite, that attracts nitrogen. So, ang zeolite, it attracts nitrogen more strongly than oxygen. So, part or all of nitrogen will stay in the bed. So, we have two stages, absorption and desorption. We have, in absorption, it's pressurization. So, part or all of nitrogen will stay in the bed, and the gas exiting the vessel will be richer in oxygen than the mixture entering. So when the bed reaches the end of its capacity to absorb, and adsorb nitrogen, it can be regenerated by reducing the pressure, thus releasing the adsorbed nitrogen. It is then ready for another cycle. So in a pressure swing adsorption, so there are two stages. We have the desorption and the adsorption. All right. So as you can see here, this yellow thing here is the zeolite. This is also the moisture absorber. So this zeolite attracts nitrogen more than the oxygen. So as you can see here, during the pressurization or the adsorption, so nitrogen is adsorbed within the zeolite. All right. So lastly, of the gaseous pollutant air pollution control, we have combustion or flaring. So flaring is a volatile organic compound combustion control process. So it only is used when there are VOCs, in which the VOCs are piped to a remote location and burned in an open flame. Auxiliary fuel and steam or air to promote mixing for nearly complete or 98% VOC destruction. So, um, the combustion or flaring, it cannot be used to treat halogenated compounds. So, halogens, we have chlorine, bromine, fluorine. Yes, those are halogens. So, the combustion and thereby the loss of VOCs produce nitrogen oxide emissions and is typically unacceptable as the only means of eliminating VOC from highly concentrated streams. So, uh, people are now industries are now transitioning to different methods other than flaring or combustion. So you can still find these in old diesel plants. So those plants have VOCs as byproduct. So they flare. So this is actually uh, an example. So this is what they do. So gas or VOCs are combusted in an open flame. All right. So why do we not use flaring to treat halogenated compounds? So we know that CFC CFCs have chlorine in them. So basically, if you treat halogenated compounds, so there will be a production of CFC. So CFC have chlorine and chlorine. So this is how the ozone layer is destroyed. So uh, there would be a free chlorine in the atmosphere and it will bond to the O3. So this chlorine atom will destroy different O3 compounds or ozone compounds with just one free chlorine. So this is actually dangerous. That's why it is not used to treat, flaring is not used to treat halogenated compounds. So this is how the ozone layer is destroyed. So UV radiation interacts with a CFC molecule, stripping off a chlorine atom. So UV radiation splits off a chlorine atom and there will be a free chlorine in the atmosphere. So the Cl atom strikes an O3 molecule resulting in a O2 molecule and a chlorine monoxide molecule. So there would be, so the free chlorine bonds with one oxygen molecule to form chlorine oxide and oxygen, or O2. A of free atom of O, oxygen, collides with chlorine monoxide, and so it also forms O2, and the chlorine is now a free chlorine and will find another O3 molecule. All right, so that's the danger. That is why it is not recommended for halogenated compounds. So this is the afterburner. So an afterburner uses a clean burning fluid to destroy organic pollutants. So fumes or vapors are passed through a jet of fire. So this actually burns the impurities. All right, so this is a catalytic converter. So in a car, so actually in a car, there is a catalytic converter. So it works the same in the car where gas or diesel or fuel is burned within the converter, just like that. So in the catalytic converter, partial combustion products or carbon monoxide is completely oxidized. So this is also a form of combustion. So that's it for gaseous pollutants. Now we have control measures for particulate pollutants. So these include cyclone, filter, liquid scrubbing, and electrostatic precipitation. So cyclone separators. So the particles exit the bottom while the gas turns upward into the vortex and leaves through the top of the unit. So this is a cyclone separator. So as you can see, the yellow particles are the particulates and we have the uh, gray particles as the air. I mean the gas. So to separate, so there would be a vortex at the center. So the particulate matter being heavier, it goes down the cyclone, while the gas being light, and it will eventually, gases, the behavior of gases will always go up. So the gases goes up and leaving it with no particulate matter. Next, we have the air filtration. So a device composed of fibrous materials which removes solid particulates such as dust, pollen, mold, and bacteria from the air. So this is actually very famous during the COVID-19 pandemic. So many people were buying already air filtration devices inside their home. So basically, the air filtration has a filter medium, a fibrous material, and air is passed through that fibrous material, and this is where the dust, pollen, mold, or bacteria or virus like COVID-19 from the air is filtered. So air filtration systems may involve impaction, diffusion, straining, or interception, and electrostatics. So how do air filters work?
How do filters remove particles from the air? It's tempting to think of air filters as microscopically small versions of kitchen sieves which block large particles from getting through while letting small ones past. As we'll see though, this picture is rather misleading. Many types of air filters are made from tangled bundles of fine fibres. Together, these create narrow, convoluted pathways for the air to pass through them. For the really large particles, these filters actually do behave a little bit like a kitchen sieve by physically blocking the particles from getting through, but this is pretty much where comparisons with sieves end. To understand why, imagine for a moment a car speeding along a winding road. The car fits easily on the road, but if it's going too fast, it won't be able to navigate the bends, and you just know that at some point it's going to crash. It's the same for small particles speeding through an air filter. As the air twists and turns, the particles can't keep up, and ultimately they end up crashing out and being caught. Because of their inertia, which just like the car depends on how massive they are and how fast they're going, they can't stay the course. But what about the smallest, lightest particles, those that can easily slip along the winding path the air takes? Amazingly, these are also captured efficiently, but for a very different reason. Because these particles are so small, they have very, very little inertia, and they dance around as they're bombarded by the air molecules around them. This rather unusual behaviour is called Brownian motion after the first person to observe it, and as they dance, they end up colliding with the filter and being captured. So at the end of the day, it's not the smallest airborne particles that are the hardest to filter out, but the medium-sized ones, those that are too small to be captured through inertia, but too large to be captured through Brownian motion. And this is why, when manufacturers design and test air filters, they don't use the largest particles or the smallest ones, but they use the middle-sized ones, those particles that are just the right size to slip through and make it to the other side.
So an example of filtration system, we have a baghouse. So a baghouse actually has filters inside the, so the polluted air goes inside these filters. So this is what it looks like inside. So these are round or cylinders of fibrous material. So particulate matter is trapped on the filter. So in time, the particulate matter um, will be blocking these filters, so they become full and they can be shaken or tapped, causing particulate matter to fall at the bottom of the baghouse for collection and disposal. Alright, so you will see this baghouses, you will see this in feed mills. Alright, so since there is a lot of particulate matter that will escape through the air, since the nature of feed mills is the use of powders and meals and stuff. So you can see baghouses there. Alright, so that is filtration. So this is an actual picture of the baghouse. So this forms a like silo at the bottom. So this is where the particulate matter is collected after. All right, so the gases go through here. You can also see that in cement manufacturing plants. Okay, third is we also have a liquid scrubber. So I've mentioned earlier that a Venturi liquid scrubber and the pack bed scrubber also these liquid scrubbers also um, remove particulate matter in uh, in particulate matter in gases. So liquid scrubbers that's why liquid scrubbers are widely used in manufacturing plants, because it does not only remove gaseous pollutants, but it also removes particulate matter. So lastly, we have the electrostatic precipitator. So how does electrostatic precipitator work? Watch this video to understand.
El- Electrostatic precipitator. The carbon and other dust particles released in the atmosphere from industries are removed by electrostatic precipitator. In this method, two electrodes are fitted against the inside walls of the smokestack. When high voltage is applied, an electric discharge takes place across the stack, and as a result, air in the stack is ionized. The ionized air consists of ions and free electrons. The free electrons get attached to the gaseous particles moving up the stack. The particles get negatively charged and are attracted to the positive electrode located on the inner wall of the stack and settle down there. These can be dislodged from the electrodes by vibration of the electrodes and are collected in a reservoir. In this way, about 99% of the particulate matter gets removed from the fuel gases by this.
So that's how electrostatic precipitator works. So basically, it by negative it negatively charges air. So voltage is sent through an electrode, while the metal plates on either side are charged with positive particles. So since the air is charged with negative particles, so it is attracted to positive electrodes and leaving the gaseous leaving the gas with no particulate matter. So this is an example of an electrostatic precipitator. So there are electrodes and inside, and also there is a there are electrodes inside of this equipment. Okay, so that's all for air pollution control. Thank you.